So, here you will see the inverse result. So, this is the inverse result. So, the input I have provided to these first joints of each leg as the trajectory I have shown you for the fiber mechanisms. Okay. Now, here if you wanted to use this program, these are Lagrange multiplier wherever I cut it. So, these are the two places I have cut it. So, 2 into 2 component, 4 components are here. These are the driving torques, okay, and these are other joint and velocities and etc. Okay. So, these are the plots of the driving torque when the manipulator is moving on a horizontal plane like this. Okay. That is why you see the symmetric nature of all the driving torques. No? Then this one is vertical mode, no? This way as you have seen in the on the screen. Okay. Now, I will show you the forward results, again going back to the same program. So, I go to the forward and I open again in MATLAB, okay, and this is inverse. So, I go forward here 3R, copy, paste, yes, and then I run and then run. Okay. If you wanted to change the parameters, there is a input file. Okay. Now, this is falling due to gravity. No? Again I did not put any external torque here, and I said okay, hey, you fall due to gravity and how it will look like. So, this is the behavior, you will get it. Okay. And if you wanted to change the numerical values in order to simulate your thing, so there is something called inputs.m. So, this file has different parameters required, number of links, then degrees of freedom, system type, closed loop, open loop, then subsystem 1 description, subsystem 2 description, so on and so forth. As I told you at the beginning of today's class, so there is a manual comes with it, you can use it, but just like any other software, even you it may look so simple, but once you get into it, it requires some understanding of the uses. So, now coming to the last thing of the parallel manipulator, the Stewart platform, or what we call 6 degree of freedom parallel robot. I have shown you a real working model in the last class, but today you see an animation of from a CAD model. So, this was developed in Adams. So, here I am showing only a rotational motion of the Stewart platform. Okay. So, if you wanted to do its dynamics, again classical method always exists, like you separate them all, and then write its equations of motions and combine them just like we did it for the forward linkage. But here since there is a special motion, each leg has 2 moving links. So, one at the bottom, one at the top. So, 2 into 6 12, and then this motion will be the 13 one. So, there will be 13 bodies. If you write all 6 equations, 3 for translation, 3 for rotation. So, there will be 78 equations, and then finding out all the reactions and the driving torques. Okay. But we do not want to get 78 equations to be computed. So, again we follow our method of cutting it here, but here if I do that subsystem approach, things are looking very odd actually. So, that is why we do something what I was proposing, that trying to maintain the symmetry as much as possible. So, this is a more or less there is another approach by Bhaskar Dasgupta, professor in IIT Kanpur. So, it is a very similar approach, but using our DNOC concept. So, here we cut it. So, one leg comes with its no, this also separate. So, we cut it here. So, this is a platform, I am showing one leg here. So, I cut this leg. So, I get 6 legs. So, 6 legs will make it 6 subsystems. Okay. And for your information, here you have a spherical joint and here you have the universal joint, okay, or the Hooke's joint, because total degrees of freedom has to be 6 in order to obtain 6 degrees of freedom on the moving platform. So, 3 here, 1 the driving motion here, and this is 2, 3 plus 1 plus 2, 6. So, what we do is we cut it here, and then once we cut it, so since a spherical joint cannot resist moment, it will only resist force. So, only 3 component of Lagrange multipliers will show up here, right, the reaction forces. So, that is indicated by this notation. So, 3 components, okay, 3 component. Okay. And then at the bottom I have Hooke's joint. So, I separate them equivalent to 2 revolute joint intersecting at one point. So, I am showing by dotted line, these are kind of a virtual links which has no mass, no link length actually, okay, and they are substituted with a 2 revolute joint, 1 here and 1 here. So, now I have 1, 2, 3, 3 degrees of freedom actually. So, this leg will have 3 degrees of freedom, 1 due to this Hooke's joint here, which is substituted with 1 revolute joint, 1 revolute joint and 1 prismatic joint. So, 3 degrees of freedom each leg has it. So, if you write constraint equation of motion, you will get 3 constraint equation of motion, right. So, this is the one I am getting it here. Subsystem 1, it has 3 degrees of freedom, I get 3 equations of motions, but how many unknowns? One of course is driving force, and then this one 3 components of the Lagrange multiplier related force. So, total 4 unknown. So, 3 equations, 4 unknowns, I cannot solve it. Okay. So, I have to take help of the other subsystem. So, you take all subsystems. Okay. So, 6 into 3 constraint equations, let us look at it here. So, subsystem 1, 2, 6 legs. So, each has 3 equations. So, into 6. So, you have 18 constraint equation, okay, but we have 4 unknowns into 6. So, the 24 unknowns. So, we have a short of 6 equations, very easy. The 7th body is still remaining, right, the moving platform. So, moving platform is one body which has all these forces coming from the legs. Okay. So, this can form 6 equations, because 3 for rotational equations of motion and 3 for translational equations of motion, but how many unknowns here in this case? No unknowns, because all these f lambda related things we have considered in our subsystem. So, no unknown. So, I have added 6 equations, but no unknown. So, we have total 24 equations and 24 unknown. So, instead of 78 equations, I can now work with 24 equations. So, if you do this manipulation here, one can get this result, that NC is a moment applied at those joints can be obtained from the that Lagrange multiplier forces, and all those forces acting at the mass center can be the summation of all this Lagrange multiplier forces coming from the legs. You do little manipulation here, algebraic manipulation. Okay. One then can write that the total moment applied on the 7th body, the moving, and number of forces applied on the moving body is equal to the sum Jacobian J. Actually, it should look like a J transpose, as per our conventional route, but I have denoted here is only J, and then the driving forces F 1 to F 6. So, then tau is equal to J inverse H, one can compute it. Once you get it, the inverse dynamics is complete. Okay. So, this is the work from a MTech work in 2009, dynamic analysis of 6 degree of freedom motion platform, and MTech report at IIT Delhi. So, using this formulation, okay, the student has developed a GUI which does not have an animation, but it has the plots available. So, here you can input the data related your 6 degree of freedom. So, sdd.xls. So, you want to see how the data is given as input here. Okay. So, open. So, it has all these parameters g, the acceleration due to gravity, the d2, the origin to the mass center length, r3 from the mass center to the next origin, the masses of the 6th platform. So, this is related to the moving platform, and then we have all this geometric information here, and then inertial information here, and all this explanation is given here. So, for your Stewart platform you have to change this data, and then you go back to the slide. So, I say run. So, run means it will run the something wrong here. Let us go back. File has not started. Okay, let us try it again. Okay, so it did the computation for you. Now, the input motion, I can take the plot. So, this is the x motion. So, there is, I have shown you that animation of atoms, it has only vertical motion z. So, that is the inverse dynamics is done. So, x motion is 0 throughout, y motion is 0 throughout, z motion is varying. So, that means I am going vertically up. Okay. You wanted to get the output results. So, output results are actuation forces, leg 1 is shown here, you want to see leg 2, this is leg 2, leg 3. So, it will be more symmetry because it is going up, all require the same effort, right. So, that is why you are seeing the same plots everywhere. 4, 5, 6, and then the reactions wherever I cut it actually. So, this is at the first x component, y component and the z component. Okay. Reaction 2, x component, y component. So, animation was not done in this interface, but the plots were available to solve the system. Okay. So, this is the trajectory I took for each prismatic joint, and these are the torque which I have shown you live from the GUI. So, that actually completes the closed loop system. At the later stages, I have shown you only the philosophical approach how to do it, but as you know the computations would be very similar to what we have done it for the simpler case. Only thing you have to sit down, spend time and get those results out before you go into the programming aspect. I wanted to show you some more animations which were done using the concept of cut loop concept. When it is a tree type system, that cut does not appear, like in the left hand side you have the planar walking machine. Now, it is a tree type system. So, cut does not appear, but in the right hand system you have the closed loops here. So, here you have a closed loop and there you have a closed loop. It is a combination of an approximate straight line generating mechanism, the green one, and the red one is the pantograph mechanism. Very interestingly, now we have used it for carpet scraping machine, but then in Italy they have used it as a walking leg. Okay. So, I show its animation here. Okay. And all those examples are there in Redism environment. This is a special biped, which means it has spherical joint at the heel and at the waist here. This is a quadruped. Now, again a spherical quadruped, at the hips it has a spherical joint. Okay. And last in this series I wanted to tell you, now people are using multibody dynamics or the robot dynamics concepts even for flexible body systems, because typically if you consider this as a rope for example or a cable, if you write its dynamics from theory of vibrations, it will give rise to a set of partial differential equations, which are not only computationally expensive, but also it has numerical issues. So, people thought of approximating this as a series of small rigid bodies connected with either with the revolute joint or the Hooke's joint, okay, or the universal joint. And to take care of its flexibility, you can introduce springs, here. If there is a damping characteristic, you can introduce, and then you treat it as n degrees of freedom serial chain. So, in this simulation what you see, it has about I think 220 degrees of freedom here, but we have done up to 1 million, no 100,000 okay, degrees of freedom. It took 17 days to run this thing, and for such system as number of links will be increasing to make it more and more realistic, the numerical issues becomes more predominant, and you require a very stable algorithm to do these things. Okay. So, with this I conclude all my 4 lectures here. I have showed you at the beginning the purpose of recursive robot dynamics. Mainly 2 aspects were there, efficiency and the numerical stability. The Dinock matrices for serial chain I have introduced, and then I have showed that how Newton-Euler equations can be converted to Euler-Lagrange equations. More formally, probably a set of constraint equation, as one of the students pointed it out, not necessarily has to be called as Euler-Lagrange, but a set of minimum constant equations of motions, which can be derived using other approaches also other than Euler-Lagrange. Constraint equations of motion for serial chain system, that is now I have formally put it. Schemes for inverse and forward dynamics, which also include the simulation. So, I mentioned to you simulation means forward dynamics, that means calculation of joint accelerations followed by the integrations would together call simulation. Robo analyzer software for robot dynamics I have shown you, demonstrated to you. Parallel robot application, I started with 4 bar mechanisms using free body diagrams. Then I have cut open system, where I have showed you subsystem recursive approach. ReadySim software, which is actually MATLAB based algorithm, I have demonstrated to you, and 5 bar 3 degrees of freedom planar robot, then Stewart Platform dynamics results I have showed you. One custom made GUI for Stewart Platform was demonstrated to you, and finally, simulation of several walking robots and rope using ReadySim was also shown. So, if you have questions in future or comments, you are welcome to contact me to this email address, and then my website, where I will also upload these lectures in future, which will be appearing under courses, and you will be welcome to see those things and comments. And as Professor Mukherjee is telling, they will be also available in NPTEL. Okay. So, if you have quick questions, I will take it before we formally close.
The Stewart platform which you have shown,
yes,
this is similar to what Dasgupta and all have done.
Yes.
Because they have also taken the platform out and then.
Yes. Yes.
So, can't it be solved by that subsystem approach where we can take, we can even cut the prismatic joints and become one link which is having a tree type system.
Okay. We do not want to cut the prismatic joint, because that is an active joint, because that is the result I wanted to calculate. Okay. So, if you cut it, then there will be severe issues will be coming into it. So, you can cut it other joints actually, you can cut one of the probably. So, you come through one leg, come here, and maybe you can cut one of the spherical joint here, or you could go down even further and cut one of the universal joint maybe, right. But it was looking so distorted actually, so we did not feel comfortable at that point of time. As you see, for 3 degree of freedom planar parallel robot, it is looking pretty distorted, right. So, one could feel scared that okay, they are not able to use the existing algorithm by running the loops from first subsystem, second, third, exactly same manner. Right. So, there we had to try a little different one using Dasgupta's approach. But the equation of motion for each leg was treated as a constraint set of equations of motion. In Dasgupta, they would be doing it more or less from the free body diagram, writing the separate equation of motion and then simplifying there. So, that simplification we are formally proposing, that you can do it through one Dinock approach.
Can we also solve tree type with some closed loop in between?
Yes. Yes.
The one which was there in carpet scattering.
Carpet scattering, yes. Yes, here. So, here we cut at some strategic location, no, and then we make it a tree type, complete tree type system, okay, and then solve it. So, that is there in this, this is actually a book converted from a thesis. No? Here the scrapping machine is solved how to cut it, so that you get a subsystem. So, here you will have different options to cut it. So, if you want to take the advantage of subsystem, you have to cut it at strategic location, and the guidelines is provided how to cut it. If no other, so thank you. Yes. Size is not a limitation here, but in this case I think it was considered as about 1 meter. In this simulation you see 20 links, but we have done up to, as I said, 100,000.
When you do integration, numerical integration, normally there will be errors which is like adding up.
Yes.
So maybe you can see it like when does it start to pop up or
When
increase the simulation timers?
Yes, actually for this kind of large number of serial chain system, no, there will be numerical peaks will be coming up in the joint accelerations. Okay. So, that is why if you use a classical one, here I wanted to mention to you a commercial software now could not solve more than 200 degrees of freedom. Okay. It hanged after 24 hours. Okay. Whereas, using our algorithm, even it took 17 hours, but it could solve it, because commercial algorithm would be very general purpose algorithm, right. It might be forming that 6 equations for each link. So, 100,000 means 600,000 equation, and from the it is not a, if it is not a recursive algorithm, then it will have peaks in joint acceleration like this, and it will not be able to solve it, and as the number of links increasing, it will go even worse and worse, and finally it will hang. Numerically it cannot solve it.
For this rope system, is it only the serial or decouple for a serial system? Is it the same thing?
Same, exactly the same thing.
Some modules and all. Is it some advantage?
Sorry?
The concepts of modules is.
Oh, this is just for understanding purpose. Suppose if you have only 6 degree of freedom algorithm already there, so then you can think of as a several 6 degree of freedom, and then start using it. So, that is the concept of module we are doing it here. Suppose if you have 6 link serial manipulator program is already available with you, and you wanted to solve this rope with that algorithm. So, then 6 degree of freedom can be considered as one module, and there will be several of such modules.
Will be dependent,
The
motion will be dependent.
No, because this is a serial chain. So, each module can be thought of as one big rigid body, and another is another rigid body, the way we formulated the rigid body formulation, and you have to just do coupling here at this chart. Okay. So, thank you and enjoy recursive robot dynamics.